So in the last video we were just talking about linear differential equations and some properties of linear differential equations, and then we saw that if we want to try to solve that differential equation, the linear, x prime equals ax, where a is a n by n constant matrix, then we start with an ansatz of e to the lambda t times v. So the only place that t is appearing in our function here is this exponential function. This v here is, we're assuming, is a constant vector. Okay, and so if we differentiate that on the one side and then multiply it by a matrix on the other side, we can put the two expressions together. And when we did that, we found that in order for this to work, AV must be equal to lambda times V, which is the definition of an eigenvalue and eigenvector. Okay, so now we're trying to solve this equation, AV equals lambda V, for both lambda and V. So how do we do that? So the first way is to go ahead and get that set equal to 0 instead of equal to lambda times V. And so we start off by taking AV minus lambda V equals the 0 vector. Because now we're solving for the null space of a matrix. Well, not quite yet. We need to factor the V out. And remember that when you do that, right, we need to actually, this inside expression is not defined, right, because we have a matrix minus a scalar. So what we really want to do is take that to be lambda I times V. And again, that's because notice that if you multiply everything back out, you do get the correct expression. Okay, good. So now we're trying to find the null space. Solve for the null space of a minus lambda I. Okay. Now, how do I know that there even is a null space for that? Well, in order for us to have a non-trivial null space, then we must have the determinant of a minus lambda I equal to 0. If not, the null space is equal to just the 0 vector, and we need something that's not 0, right? Because if the determinant was not 0, then a minus lambda I would be invertible, and in that case the null space of an invertible matrix is just the 0 vector. Good. Okay, so this was called the characteristic equation, and it is, if you were to expand it out, a polynomial of degree n, right, in lambda, meaning that the determinant of a minus lambda I is going to be, you should be able to write it as lambda to the n, well, plus or minus, right, lambda to the n, well, we'll just say plus c1 lambda to the n minus 1 plus c2 2 times lambda to the n minus 2 plus lambda, cn times lambda plus cn plus 1. Okay, I didn't really have to write all that out. But I wanted to emphasize that because this is a polynomial of degree n, we can factors into a product of linear factors and quadratic factors, where the quadratics are irreducible. Is this sounding familiar? Because what we're saying is that all polynomials, all real polynomials, can be factored into a product of linear factors. By linear factors, I mean factors of the form like ai times x minus bi. And then quadratic factors are just irreducible quadratics. Okay, that's because this little factoid comes into play when we're starting to talk about partial fractions. because the way you the way you break down a partial fraction depends on whether you have linear factors or irreducible quadratic factors. And then we could have repeated linear factors and repeated quadratic factors. In our case, it doesn't matter. Well, I guess I shouldn't say that. It will matter. um, so another definition here while we're at it. An eigenvalue, which is a root to this polynomial, has algebraic multiplicity k if something like lambda minus whatever, maybe I'll say it this way, lambda equals some constant, lambda, if this is repeated k times. I don't know how we want to write that. K repetitions, k repeated root. Okay, so an algebraic multiplicity is how many times the root appears as a solution to the quadratic, or not quadratic, I'm reading the quadratic there, to the, what do you call that? Characteristic equation, yes. Now, an eigenvalue has geometric multiplicity k if the dimension of the null space of a minus lambda I equals k. So where does that come from? Well, that's because for each lambda, right, you have to put it back into a minus lambda I, and then you have to solve for this equation, right? And solving this equation means that you are looking for a basis for the null space of a minus lambda I. Right? Those are equivalent things, right? Solving this equation and finding a basis for the null space. Good. So the dimension of that null space is the geometric multiplicity of an eigenvalue. And so if the algebraic multiplicity is not equal to the geometric multiplicity for matrix A, then matrix A is said to be defective. And defective is going to be bad in our case. Okay, so before we go any further, maybe we need to just remember the difference here between these two things. And so a quick example is for a matrix, let's say 1, 0, 0, 1. And another matrix over here is going to be 1, 2, 0, 1. Okay, now lambda is 1 and 1, so this has algebraic multiplicity equal to 2. And here lambda is equal to 1 and 1 with algebraic multiplicity equal to 2. Okay, so if I go into this first matrix and look for the eigenvectors, then I see that A minus lambda I is just going to be the 0 matrix. And so the null space of A minus lambda I, well, I don't need the ESP there. The null space of the 0 matrix is going to be every vector. And so let's just erase that. So we want a basis for R2, so just pick any basis. Standard basis is always a good one to choose if you're just looking for an arbitrary basis. And so the idea, though, is that the dimension of the null space of A minus lambda I is equal to 2 in that situation. And so these two things are equal, right? But over in the other situation, if we take a look at A minus lambda I, we end up with that 2 sitting there. And so now if I look for the null space, I get that 2v2 is equal to 0, or just v2 equals 0. And so I have this extra condition now. And so now the only vector that works is the 1, 0 vector, right? Or a scalar multiple thereof. And so in this case, the geo multiplicity equals 1, but the algebraic multiplicity was 2. So these two things are not equal, so this is called a defective matrix. Okay, and so the only thing that we have to do now is maybe do some numerical examples. Probably the hardest part about doing these by hand, right, is just to be able to factor out the polynomial that you're given. Well, creating the polynomial and then factoring it can be a pain in the neck. So we'll typically only do 2x2s when we're doing it by hand, but when we're doing with or maybe a real simple 3x3, nothing too complicated. So we'll take a look at a couple in the next video.